So what I've done is I've done a mid-course correction to try and see whether we can focus a little more on the models. So today we're going to be looking at uncertainty, and rather than spending too much time on the algorithms, I've decided that it would be good for us to get an exposure to how to deal with uncertainty. And then tomorrow we'll talk about hierarchy and other types of competitive structures. And so the goal today is to expose you to how to model uncertainty in the context of both decision-making problems. We need to kind of give you some overview on that, and then move to the game-theoretic regime. Okay, and then we're going to talk about how to recast this whole framework within. So if you have a stochastic Nash game, the variational conditions then become a stochastic variational inequality. So I want to expose you to that, but we won't spend as much time on that. But the hope is that at least I can expose you to that, and then look at a more detailed example regarding how to derive existence statements. Okay, so that's the plan. Let's see how much of that. So there are parts of this, because what I had to, since I had to do a course correction, there's some extra slides here which I won't be going through because I've had to kind of add some stuff, and so I haven't removed some of the proofs because I wasn't sure how much of this material I needed to cover. So there'll be some proofs which I'm going to just skim over or just completely ignore. Okay, so forgive me for having a little extra here. Okay, so one of the crucial aspects in this material is, of course, the role of convexity when you're dealing with uncertainty. So we'll be looking at convex problems afflicted by uncertainty, and these lead to often monotone stochastic variational inequality problems. The other avenue for dealing with uncertainty is robust optimization. There has been some work, we've done some work, and there have been others on looking at getting robust solutions to Nash games. But I won't be talking about that here. And then there are a host of other applications that go well beyond game theory when you use these types of techniques. Okay, so convexity, as you notice, has been crucial, and it will continue to be used during the remainder of this course. Okay. So let me just talk about how to model uncertainty. Okay, so so what I need is, I want to talk about two models, and then I'm going to give you a quick discourse on the notion of expectations, the underlying probability space, and a quick exposure to Sigma-Algebras, and just the analysis that you need without burdening you with too many of the details. So in the prior set of problems, we had parameters that were known with uncertainty. So for instance, when you were faced with when we were solving the Nash-Cournot agent problem, we had this problem. So we had this problem. Okay, and the crucial aspect was that both the cost function and the price function were assumed to be deterministic. And in fact, even the capacity was deterministic, right? Now in practice, what happens is that the cost function might be afflicted with uncertainty. Price functions need to be estimated, and capacity, as you often know, is something that you only know in some probabilistic sense, particularly if you're working with wind, right? So the question is, how do you contend with this rampant uncertainty in these problems? So let's start with looking at some decision-making models, and not all of these are relevant for your problems, but some might be, some might not be. So given a function f of x psi, we look at a situation where this is no longer deterministic, but is now a random variable. What does it mean to have this parameter here? Okay, so if psi is a random variable, then your cost is a function of your decision and this random variable. Okay, and given that you've got now a random cost, The question is, how do you minimize a random cost? So the way we minimize or we optimize is we look at some sort of avenue for averaging or contending with the uncertainty. One way to do that is to use an expectation. What the expectation does is it averages over the uncertainty. That's not the only way to deal with uncertainty. You can use a risk measure. The risk measure would also take a cost and then provide you with some sort of risk-adjusted output. Okay, so for the first part of this, I'm going to be restricting my interest or my focus to expectations. So given that I have a random cost, right? So in a random, what I mean by that is for a particular decision, this cost is given, it has an associated probability density function. Let's call it F, not F. Okay, and now the issue is that if you take a decision X, the cost could be any of these values, right? It could be any of these values, C of X psi, right, for a given cost, for a given decision. So the question is, if you want to optimize, one way to optimize is say, minimize the expectation. Or you might want to say, I want to minimize one of the quantiles. So there are a host of ways to deal with how to manage uncertainty in terms of a decision-making framework. Now, there are settings where psi is unavailable, and all that we know is that there's a parameter that appears in the specification of the cost that needs to be addressed in some way, right? So, for instance, you might have a situation where you have a particular parameter, but you don't have an associated probability distribution. Now, you might say, why don't you have one? Well, you may not have data. There are a variety of reasons why you might not have one. So one avenue to deal with that is to use a conservative approach where you say, instead of minimizing the expectation, I'm going to minimize the worst case over some uncertainty set. And this is a user-specified uncertainty set. So for instance, in this particular case, what I say is, suppose I have psi, I assume that psi takes on some value between some interval, right? It might be some, and so I want to minimize this worst case or this worst case, whatever that might be, okay? Might be here or whatever. And that's given by what we call, so this is, now one of the problems with this, and I won't be talking about this in this class, but what you have to recognize is whenever you have these types of models, they lead to conservative solutions, which is fine. But from a mathematical standpoint, they're often quite difficult to deal with. The general avenue has been to take this and use duality theory to recast this as another convex optimization problem. There's also been some work done in the context of variational inequalities, where the question is, if I gave you a variational inequality problem where the mapping was parameterized by some vector for which we didn't have a distribution, what is the notion of robustness in that setting? Right? So in this setting, we have a notion of robustness. This is the notion. I want to minimize the worst case over this uncertainty set. That's the uncertainty set. In the case of VIs, there is a notion. One notion is that I want to minimize the worst case of the gap function. Remember we talked about the gap function yesterday? The gap function specifies whether a particular point solves a VI, right? A particular vector. Now, if you pick a vector for every realization of psi or every value of psi, you get a different value of the gap function. So you'd like to get an x such that the worst case of that gap function is minimized. Okay, so that's one possibility. Okay, so, but as I said, we're not going to focus on robust optimization or robust solutions to games in this class. So I'm going to consider the classical news vendor problem to motivate my decision-making problem. And then we're going to be able to introduce that within the competitive market problem. Okay, so I want to just give you a quick detour on probability spaces because we're going to be using this notion. So when we talk about probability spaces, we have what we call a triple, which is omega, the sample space, script f, or just f script I'll call it, is the sigma algebra, and p, which is the probability measure. And this construct helps capture processes, either real or synthetic, that are characterized by randomness. Right? Now, the space is constructed for a particular such process, and on every occasion this process is examined, both the set of outcomes and the associated probability are the same. So what I mean by that, just in terms of layman's language, if you assume that you're looking at the distribution of wind, once you've built that distribution, every time you run the model, you always believe, or at least you work under the belief, that distribution is the same. Right? Now, the realizations that you get from it when you generate it might be different because you haven't sampled enough. But the distribution stays the same. Okay? And that's not because somehow we believe the distributions stay the same. Distributions may be changing over time, right? Because of climate change, who knows what. But from our modeling standpoint, we make that assumption. Now, you could weaken that assumption. You could say that the distribution itself is evolving with time. But that leads to a harder problem to deal with. Okay? So, in the context of a particular experiment, we have this notion of a sample space. So, a sample space, and I'm going to give you examples of this. Okay? So, a sample space is a non-empty set that denotes the set of outcomes. Right? So, for instance, if I talk about tossing a coin, the set of outcomes is heads or tails. If I talk about an experiment where I toss a coin twice, then the set of outcomes is heads, 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 tails, tails, heads, and tails, tails, if the order is important. Okay. Now, so this represents the set of outcomes of the experiment. The sigma algebra denotes a set of events, and I want to make sure that you distinguish between events and outcomes. So the event represents a set of 0 or more outcomes. Okay. So for instance, one of the events I might introduce when I toss a coin twice is the event that I get one or more heads. Okay. So that would take 3 of the outcomes: heads, 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 tails, tails, heads. Okay. Now, for each of these events, I have an assignment that goes from the event space to the probability space. Right? So I basically to the 0, 1 line. For every event, I have this map which tells me what is the probability of that event. Right? So for instance, if the event is 0 heads, right, when I toss the coin twice. So this probability measure measures the probability of that event. Okay? So this is just a framework for capturing this. Okay? So once the space is established, then nature selects an outcome omega from capital Omega. So when you start working with uncertain problems, you need to establish what that space is. Okay? And once you do that, and you have a model, then it's clear to the readers and everybody who's reading your work where the outcome in the uncertain, the uncertain future is coming from. Okay, so it selects. So, for instance, in the context of, so I'll give you examples. Right. So all events that contain omega as one of its outcomes are said to have occurred in the future. Right. So if that's what you're focusing on. Now, if nature selects outcomes infinitely often, then the relative frequencies of these occurrences correspond with the probability measure. So, for instance, if you ran this experiment of heads and tails, infinitely often, what you'd find is that the number of times you see a heads versus the number of times you see a heads is getting closer and closer to 50%. Right? So it needs to correspond with that probability measure. So there is this underlying experiment that's occurring. Now, what are the properties of the sigma algebra? The omega, which is the sample space, which is the set of all outcomes, lies in F script. F is said to close. F is said to be closed under complementation. So if a particular set A lies in the sigma algebra, its complement set also lies in the sigma algebra. To give you an example, if I said that I'm interested in the double toss experiment, so if A represents the event that there's one or more heads, then A complement represents the event that there is zero heads. Okay, both lie in the same. Background standpoint, I won't be using this, but I think it's useful for you to see it. Because when you start modeling these problems, you should at least understand what the underlying mathematical foundation is. Right? I think that's important. F is closed under countable unions. So if you have a collection of events AI which lie in the sigma algebra, then the union of AI also lie in the sigma algebra. So if you take A1 as zero or more zero heads, and if you take A1 as one or more heads and A2 as two heads, now you can see that the intersection of these is not necessarily empty, but the union lies in the sigma algebra. You also have some properties in the probability measure. So the first one is it's countably additive. All that means is that if I've got an infinite collection of events, the events do not intersect. So if you have zero heads, one head, so it's heads and tails, tails and heads, that's one head, and two heads only. Those are all three sets of events or three events. Their intersection, they're disjoint. So AI intersection AJ is the empty set. Right? So then the probability of the union is equal to the summation of the individual probabilities. Right? And that's natural because the events don't intersect. Right? So so if this is the sigma algebra, and if you've got events A1, A2, A3, A4, and these are, you might have all, more of course. The probability of is equal to the summation of, okay, so it's just a property of the probability measure, and the measure of the sample space is 1, or probability of omega is 1. Okay, so that's a quick blurb on the sigma algebra. Here's a quick exposure so you understand what these mean physically. So if you have a single coin tossed, then the sample space is yes?
So regarding the last part, so that means that the event doesn't interact, so doesn't affect them?
So these are in this case, they're disjoint events. You see this? We're looking at a set of AI, which is a countable collection, so you can attach it to the set of non-negative integers. But AI intersection AJ is the empty set for this. In general, events don't need to be disjoint, but in this case, where I'm looking at this statement, they are. Okay. I'll give you an example. Okay. So in this case, the sigma algebra contains how many events? So the sigma algebra, remember what the sigma algebra is different from the outcomes. Sigma algebra says that basically the event, so you could have a heads, you could have a tails, you could have a heads or a tails. Okay, or you could have nothing. Now the probability of having nothing is 0. The probability of having a heads is 0.5. Probability of having a tails is 0.5, and the probability of having heads or tails is 1. Okay, so heads or tails is also an event. Okay, now if you look at this, Jorge, your question, these two events are disjoint, but clearly these two are not disjoint. Okay, so if you take the union of heads and tails, that's equal to the summation of the probabilities. So the probability of the union is equal to the summation of the probability.
Equivalent to use the bar with the events, I do one and I keep it out.
Exactly, yeah. So you can't have a situation like this one where if you pull it out, this still overlaps with it. If you take the double coin toss, then omega is HH, HT, TH, TT. Now in this case, the sigma algebra contains 16 events, and that's the entire listing of events. So remember, in this case, what happens is you can get heads, heads, tails, tails, heads, tails, tails, heads. That's the immediate one. Now, you could also say the event of seeing the same outcome in both tosses. That's heads, heads, or tails, tails. Or you could see the outcome of having at least one head. That's heads, heads, or heads, tails. So you can just generate all of these, right? This is the outcome that you have at least one heads in all of the tosses, right? Here the heads has, here this is the outcome that the second toss has to be tails. So each of them, there is a possibility. So you can list these out, and clearly some of these are disjoint, some of these are not. Yes?
So if I understand correctly, so this F allows us to kind of enumerate all the possible outcomes.
Events, yeah.
Does this...
Not the outcomes. The events comprise of, so if you look at this, right, what is these are outcomes.
Yeah.
So when you basically run the experiment has an outcome. So if you toss a coin, it can only take on heads or tails. But and that's what the sample space shows. So the term outcome is reserved for that. The term event is basically something that takes unions of outcomes, okay, or unions, or basically some relationship.
And in both these examples, the outcomes themselves are independent of each other. There's no sequential relation, or there's no dependent.
No, in this particular case, what you have is that when you run the experiment, first of all, they're independent draws or independent realizations. Now, each of these events, so you have to be a little careful, right? When you talk about independence in this case, the thing is that these events are not necessarily disjoint. So you have to be a little careful. So if they're disjoint, then they're mutually exclusive, right? So you have some properties, but I don't want to get too caught up in that. Okay, so here you can say that the probability of A1, so this is there are three events, and the probability of the sample space is one, where A1 is this, A2 is this, you can see. So you can go through it. But I just want to make sure everybody understands, because when I state some of these results, I'll talk about the existence of some probability space. Right now, from the standpoint of your own modeling, you don't have to worry about it as much, but you at least should know that this is an underlying object that you'll come across when you read papers in this area. Okay. So now, given a random variable, given a probability space, so whenever you define a random variable, you need an underlying probability space, because a random variable maps from the sample space to the real line or to the Euclidean space. Okay. So for instance, nature generates an outcome from omega. Your wind availability is the random variable that maps from that to the speed that you see, or something of that sort. Okay. So whenever you talk about wind speed, you say it's a random variable, but when you say random variable, what is it mapping from? Well, it's mapping from some sample space and giving you a non-negative number, which is the wind speed. Okay. Similarly, if you look at these, the solar availability that you might have, again, another random variable. If you look at demand for electricity on a given day, there's some volatility in that, right? So you can again capture it in this form. Okay, so X is a random variable, maps from omega to E, where E is some measurable space. More specifically, the probability that X, a random variable, lies in S. So whenever you talk about a probability, it's really you're counting the set of omegas that make something happen. So if I ask you, what is the probability that the wind speed is greater than 100? Right? So what you should be thinking is, what are the probability of omega in capital omega such that W of omega is greater than 100. So how many outcomes from this allow this to happen? Right? And what is the probability mass that corresponds to it? Okay. So for instance, in the context of coin tossing, if I defined x omega as 100 when omega is heads and negative 100 when omega is tails, and if I said what is the probability that x omega is equal to 100, you would say half. Okay. Okay, so now that we've understood a little more about probability spaces and random variables, let's talk about a canonical problem called the news vendor problem, which will provide us with a vehicle to start looking at two-stage models. So one of the areas where uncertainty arises commonly in electricity markets is in the need for sequential clearing. So whenever you compete in electricity markets, there's a notion of multiple clearings of the market. So you might have a forward market, a day-ahead market, and based on where you are in the world, these markets might differ. But in general, you will have some sequence of markets. It may take on somewhat different forms. And when you're competing or optimizing in these markets, so if you compete, you have multiple stakeholders, but before you understand how multiple stakeholders interact, you need to understand how a single stakeholder optimizes across these markets so that you can then model it across multiple stakeholders. So let's start with this very simple news vendor problem, which forms the core of lots of stochastic optimization discussions. So suppose a company has to decide its order quantity given a demand. So basically, a company has to decide how much to order given that it has demand for a particular item. So imagine that it has to sell, or it has to service demand for a particular type of widget. And for it to service that demand, it needs to make this widget, but the widget requires some raw materials. And now what happens is every time it places an order, the cost of placing the so for each unit it pays C dollars. But what happens is that if it orders too much, and the demand is less than what it needs, right? If the demand is less than what it needs, then it needs to place a back order cost. So if the demand is less, it needs to store it, and the demand is more, it needs to place a back order. What that means is basically you had a demand for 100, you only had 80 items, you need to service the next 20 tomorrow or day after tomorrow, whenever that is. So the term news vendor comes from, basically it's a news vendor who's deciding how many newspapers to order. It doesn't know the demand for newspapers tomorrow. When tomorrow comes, it has to service that demand. So if the news vendor orders 100 newspapers, the demand tomorrow is 120, then you might have to service the extra 20 later in the day or whatever, what have you, right? Alternately, it turns out that you ordered too much. You ordered 140, the demand turned out to be 120, which means the remaining 20 have to be stored, or you get some salvage value, whatever, right? So essentially, given that you have uncertain demand, you need to place an order for newspapers. The order, if you place, anyway, the cost of newspapers is C. So C times X is your ordering cost. If demand exceeds the number of newspapers you've ordered, then you need to back order newspapers and deliver them later in the day at a cost B. And if the amount you order exceeds demand, then you need to hold on to this, store it in some way, and get rid of it, and that holding cost is H. So the plus just says, so what is plus? Plus just means the excess when the argument is greater than or equal to 0. So if I said x minus d plus, that's effectively max of x minus d and 0. So that's equal to x minus d when x is greater than d, and 0 when x is less than d. Okay? Okay. Questions? Are we? Okay, so let's continue. So now the question is, in such an instance, the firm will solve this problem. It should be f of x comma d in that, I'm sorry. Now, let's assume that d is known with certainty, just for at the outset. So somebody magically, furnishes a crystal ball and says, well, the demand for newspapers is going to be whatever. So you know what it is with certainty, right? So in that case, so we'll start with that, but let me go through it first. So more specifically, suppose demand is a random variable defined as d of omega, where d again maps from omega to r plus, okay, and omega is a sample space. Okay. Then the random cost associated with demand d omega is cx plus b times d omega minus x plus h times x minus d omega plus. Why do I say it's a random cost? Because for every realization of d omega, I pay a certain cost. I don't know what the realization is ahead of time unless I make that assumption. So given a decision x, my cost is random. Okay, so I cannot predict my cost with certainty. All I can do is I can predict it I only know it in some expected value sense. Okay, I'm going to assume for the present that I know the probability distribution so I can compute the expectation. So stochastic programming models work under the premise that you have access to this probability distribution. You can, in some settings, you don't have this. And so when you don't have it, you can, of course, collect data to get some understanding, or you can just average to kind of get some understanding of what the average looks like and use that as a proxy. Okay, but I won't go into that now. Okay, so now since the cost is random, one avenue for dealing with uncertainty is to minimize the expectation. Not the only avenue, one avenue, right? You might want to minimize, as I said, some risk-adjusted cost. Okay, so this is an instance of a two-stage problem with recourse, right? So when I say recourse, recourse represents the ability of responding to uncertainty once that realization of uncertainty has been made evident to you, right? Given a first-stage decision. So your first-stage decision is that the quantity that you order. The second-stage decision, omega-specific recourse decisions, are either, so in this case it's actually d omega minus x plus, which is, or z omega, which is x minus d omega plus. Okay, and what are these decisions? These decisions are how much you should back order or how much you should store. Okay, so I want to make sure everybody understands this notion of recourse. Let's give you another example. So if you're competing in a sequential market, you make a first stage decision where you submit a bid to the day ahead market. It's a financial bid, right? And now in the real time, what happens is that you see, there is more information. It turns out that, I don't know, the price of natural gas has risen and you want to change your bid slightly, right? And that's a recourse decision and it has to be taken contingent on your first stage bid, right? So there are some markets in the US where there's something called a deviation penalty. So if you made a bid of 100 megawatts and you decide to change it by a significant amount, then as that amount grows, you get paid, you get charged a deviation penalty, right? On the other hand, if you don't have a deviation penalty, you can make an arbitrary change. Okay. Now there are some markets which also say that you need to make sure that most of your commitment is done in the day ahead. What I mean by that is that you can't have significant changes in your day ahead, right? So you can't show up in real time and say, after bidding 0 in the day ahead, right? You need to show up in day ahead because they need to understand what the participation levels are. So there are a host of rules. That's not something that I spend as much time on, but there are others who know a lot more about these types of rules. Okay, so the recourse decisions can be taken upon the revelation of uncertainty. And what I mean by that is when you run the experiment, one of those omegas is realized, right? If you run the experiment once, one of the omegas is realized. Upon realization of that omega, a recourse decision is taken. So take a first stage decision. There's an omega realization, and then you take a second stage decision. Right? Now, what happens is that when you take a first stage decision, you pay a cost C of x. When you take a second stage, omega times y omega. Now, the problem is that you don't know the omega that's going to occur. So, if you had to add the two of these, would this be a fair characterization of the cost? Or why not? You don't know. How do you deal with that? So the expectation could be 1, right? And the Cx comes out, so it's just Cx plus the expectation of d omega. Okay. Now what makes it harder is that the recourse decision is actually in a constrained setting, right? So the recourse decision is based on the capacities, on the constraints that you have, and those constraints may also be afflicted by uncertainty. Right? So in the second stage, it may so happen that your capacity is unavailable because there's an outage. Right? So we're going to talk about how to deal with those types of problems in a decision-making setting. Okay, so now one of the issues is that when you write out the expectation, all of you have probably taken a course in probability in your undergraduate. You remember that when you have, so imagine if I gave you a continuous random variable, like a uniform random variable, right? It has an associated density and a probability distribution function. How do you compute the expectation of a random variable in general when it's a continuous random variable? What do we do? So if I gave you, so this is something you probably remember from your classes. If I gave you a uniform 0, 1 and I asked you to compute the expectation, it's an integral of x with respect to the density, right? That's what you do, right? But now the issue is this integral. Now in simple cases, it's, you can deal with it. In very complicated cases, this integral might be nasty, right? So ideally what you try and do is you avoid integrating, and the way to avoid integrating is to approximate the problem. So you approximate the problem by generating samples from omega. Okay, so you have an oracle that spits out samples when it's probed. If you wanted k samples, you could get k samples. We work under that premise. Okay. So you get samples d omega 1 to d omega k. And then if these samples have probabilities pk, often they're just of equal probability, so pk is 1 upon k. This represents a proxy for the expectation. It's a sample average, right? So if you had the expectation of f of x omega, you might say, oh, instead of that, let me generate k of these, and I'm going to work with the sample average. What do we know about the sample average? Under nice conditions, the sample average converges almost surely to the expectation as k goes to infinity, right? So if you get k to be large, and that is the law of large numbers, right? So if you work with a relatively large k, then you're reasonably sure that's a good approximation of the expected value. Okay. Now, one of the aspects that we work on in the algorithmic context is we try and get a solution of this problem. Because one of the issues is that we don't always have a good idea how fast. So we know that we have central limit type results which tell us about how fast sample averages converge to expectations, right? Just by the standard square root n type results. But if you solve this problem, then your approximation is always, you always have an approximation. one of the goals from an algorithmic standpoint is to generate solutions, sequences that get solutions of this problem in the limit. Okay? So if you want an arbitrarily accurate solution, you have the ability to do so. Okay? So those are sampling schemes. If I get an opportunity towards the afternoon, I'll talk about how some of the methods from yesterday, the projection method, without burdening you with too much of the mathematics, how they can be extended to deal with this simple problem. Relatively simple. Okay. So now the recourse-based problem, this is the cost of the recourse-based problem. Okay. And now let's see how to model that from an optimization standpoint. Right? So from an optimization standpoint, what you have is f of x omega is cx plus b times d omega minus x plus h times x minus d omega plus. Okay, so let's write that out. I want to make sure everybody sees that, and we'll figure out how to solve that as a simple linear program. Okay. So I have minimize Cx, okay, plus, what did I have, P, B, backward. I'm just going to call this dj. This is j equals 1 to capital K, holding cos. Now, whenever you've got, let me give you a quick kind of modeling trick. Whenever I'm minimizing something like this, right, and I say, let's just say x is greater than 0, right? So this can be written as okay. But now what I do is I define this as some v, and I say minimize v, where v is the max of these two. So v is greater than x minus d, v is greater than 0, x is greater than 0. So now I have this problem, it has an extra variable compared to this problem. Can someone tell me why this is a useful avenue? Why is it a useful avenue to actually do this? Yeah, so it's a linear program. This is easily processed by most solvers, right? And it's got a lot of smoothness properties that you can leverage. This, on the other hand, has a non-smooth objective. It's still convex, but it's a non-smooth objective. So in a lot of cases, not all, right? If I had a min x minus d, it wouldn't work, because then you're minimizing a concave function. Okay? So when you're minimizing a convex non-smooth function where there are a finite number of kinks, then you can do this quite easily. It turns out, in this particular case, if you add variables, what you're left with is minimize HWJ, and then you just say Vj is greater than, now remember what this is. This is Vj, this is Wj. Now let me ask you another question here. I told you that V is greater than x minus d and V is greater than 0, which means V is greater than max of x minus d and 0. But remember what I'm trying to minimize. I'm trying to minimize the max of x minus d and 0, not something that is above max, that is an upper bound on max x minus d 0. Why is this still correct? Why is it correct that I'm minimizing this and I get a solution to that? The constraints are right, but why is it that this will give me exactly what I want?
Because
So if you but you're greater than, how do you know you'll be at the maximum?
One of them will be always by zero.
So the thing is that you're minimizing V, right? So if it turned out that I got a solution V, so you can argue this just by simple contradiction. Suppose at the optimal I had this holding, right? But then I could come up with something which is V tilde, which is less than V and greater than max V minus D 0. Not V minus D, X minus D. Right? And this would have lower cost. And I could continue in this way till V tilde became equal to that. Right? So you want to make sure that when you have these types of arguments, you want to argue them in a fashion which has mathematical rigor so that you can explain them to whoever. Yes?
So this works when you have like a simple objective function.
Yeah.
If you have a more complicated objective function, it's not always the case. Do you have like a easy trick to...
Yeah, so for instance, if you're minimizing, as I said, if it's a concave function, so suppose I told you I'm interested in minimizing the minimum, right? So in this case, if you drew out that function is something like this.
But even if the objective is...
So you could also have composite a composite function like this, h of x plus. So would this work?
So if h of x is convex, theoretically, yes.
Yeah. So if h of x is convex, you do exactly the same thing. The same argument will allow you to claim that this avenue works. The main problem is when you have concavity. That's where you have to be careful. So what I mean is in the objective, if you had a convex function with kinks, in general you can deal with it. If you have concave functions, you can't deal with it. Yeah. Now, if you had a max function, suppose you had this function. Y transpose. Could you do something with this? So the problem with this is that this is if X is a general set, then if you wanted to replace this, right? If you said, okay, let me replace this by h of x plus v, now you might say, oh, I can just write this. What does this do? So actually the constraint is bilinear, and the other problem is that it's semi-infinite. So there's, if X is a general closed set, you need an uncountably infinite number of these constraints for this to work. You can still get it to work, but then what you have to do is if this holds, you have to say V is greater than this, that means V is greater than the supremum of this. And then you have to be able to optimize this. So for instance, one setting where this holds is if you can actually compute this using calculus. But if you have this constraint, you can't do that. Right. So in general, and in fact, that's what robust optimization does. It actually uses duality, and comes up with a single constraint by using duality theory. So in general, what I think is a useful trick is to see, first of all, if you're looking at maximizing, then are the points that you're maximizing over finite? In which case you can, and if they're not too large, you can replace them by constraints. If you have something that you're maximizing over is actually from a set, then it's a little harder, and it really is case dependent.
So I'm working on a couple of programs. One is very similar to this, but with the risk manager and problem. And one
Is that the conditional value at risk?
Yeah.
Okay, so the conditional value at risk, there are 2-3 things you can do. I'll talk about that later. So it's so with the conditional value at risk, there are some. It actually may not be a bad idea to just keep it up there, and I'll show you how to deal with it. So if you use, and so once I give everybody enough background, and we can have a discussion. But the issue is that with a conditional valued risk, if you're taking the expectation over a general measure space, then you need to have as many constraints as there are realizations of uncertainty,
Yes.
right? Which means it's semi-infinite if the expectation is over general measure space. So better idea is to keep the expectation, keep it back up there and smooth it. And I'll show you, I might do some of that offline if you want, we can talk.
Absolutely.
So now what you've done is we've written it like this, and we said, there's no free lunch, right? Once you do these things, you are paying for it somewhere. Let me show you where you're paying for it. So Vj is greater than b times dj minus x. Vj is greater than 0. Wj is greater than h times x minus dj, and Wj is greater than 0. And this is from j equals 1 to k. So now you made this into a smooth problem, but what have you paid in that process? What do you think has happened? What has changed in this problem? So in the first problem, how many variables did you have? Just one variable, right? One variable with tons of kinks, right? And now how many variables do you have? You have 2k plus 1 variables, right? 2k plus 1 variables. What else do you have? Yeah, you have like 4k constraints, right? So you've basically made your problem massive, right? But we know that even if the problem is linear but massive, you can still solve it. In fact, nowadays, Cplex or Gurobi can solve linear programs of the order of hundreds of millions of variables and hundreds of millions of, and when you have binary variables, it's obviously less, but still, linear, you can do a lot. However, you don't want to take too much advantage of that. So you don't always want to do this. So to Fabio, right? Mm-hmm. To Fabio's point, sometimes if you have an expectation, a better idea, instead of, because what do you have? You have a kink like that. A better idea sometimes is to smooth it and then to drive the smoothing function to the original by using, so there the algorithms have to be a little more refined. So you can do that. Right? So we've been working on some of those things, and there have been others working on these questions. But sometimes just replacing it by adding constraints doesn't scale.
Yeah.
Right? So we can talk a bit about that. Okay. So does everybody see what I've done here? So this is a stereotypical problem that arises in energy markets, in coupled energy markets. But it's actually free of a lot of the complexity in the future. And I'll bring that in as we proceed. Now let's consider the news vendor problem again. Now this news vendor problem can be written as the cost of making decisions today or now plus the expected cost of responding to uncertainty in the future or taking recourse. Okay? So that's why we call it the expected cost of taking recourse, or just the, I'm just going to call it the recourse function. The recourse function is the cost of taking recourse. So when I say the recourse function is the expected cost, the random recourse function is the cost of taking recourse given a decision x and a realization omega. Okay, so Q script of x omega is the cost of back ordering or holding given that the first stage decision is x. Okay, to put it into the electricity markets parlance, what that means is, suppose I've made a day-ahead decision. The cost of taking recourse is given by the cost of either bringing on new capacity or paying some penalty to modify this first stage decision. Okay, in some context, right? But in other contexts, it might be more intricate. Now, in this particular case, you can see y omega is quite simple, z omega is quite simple. But in real markets, you might have to deal with network constraints. There are a host of things that appear in this second stage problem. In some cases, you have to worry about physical constraints here and not in the day-ahead market. Okay, so we are working on some AC power flow modeling where you have two-stage stochastic power flow, where we have to deal with some sort of complementarity requirements only in the second stage. So in this case, the second stage problem is still nice. It's a convex problem. There will be instances where this problem is actually non-convex, right? And you have to deal with it. Okay, but I don't want to go there yet. Let's just deal with the nice world. Yes.
Is there any reason why in this you have two variables for the two-stage, for the second stage, whereas in the previous slide that you showed you had just one?
No, I had two. Oh, okay. Here I actually combine, and so you can actually reduce this to one set of variables, but it's just cleaner to have two. Yeah. Okay, so does everybody understand? This is crucial. Does everybody understand what the cost of taking recourse, how you formulate it, model it, and where it emerges from? So it's Q script of x omega. It's just the cost of taking recourse in the second stage, given that the decision, the first stage decision is x, and the realization of uncertainty in the second stage is omega. Okay. Now, this motivates a canonical form for the two-stage problem. And this is all linear, okay? So in the linear two-stage problem, you take a first stage decision x, and you have a second stage expected cost Q script of x omega. Your first stage decisions, your day ahead decisions, might have some requirements. You might have to meet some capacity requirements. Maybe you have to meet physical requirements. Some markets might impose that, okay? And this Q script of x omega is your second stage cost. And let's look at the second stage cost a bit. The second stage cost requires you to meet feasibility. So for instance, if you've taken a day ahead decision, your second stage decision has to be taken so as to meet some random demand. So this is also, this h could be random, right? Similarly, any change that you make is penalized in some way, right? And of course, you have to meet some sort of non-negative requirements, if at all. Right? But more generally, you can capture this as a linear program. Okay. Now, it's not essential this be linear. This could be generalized to convex. It could be generalized to non-convex. Right? Just the framework becomes a little nastier. In fact, you can even have other formulations, and this is what Zhongxi has been working on, where they change even some of the aspects of the where the uncertainty arises and where y shows up. And where x shows up. So x could show up here, problem becomes harder, becomes non-convex, right? So you can do lots of stuff with these problems, but this is just a framework, okay? Now, the issue is, so can someone tell me what the issue is? Now, given that, so I've told you what Q script of x omega is, right? If Q script of x omega was 0, how easy is the first problem to solve? How easy is it to solve? It's just a linear program. You've been solving those since yesterday or day before yesterday, right? That's easy. If I told you what Q script of x omega is in terms of the second stage problem, how easy is it to solve? Can you formulate it? How would you formulate it? It's not evident, right? Because if you wanted to formulate it and put it into MATLAB or wherever, I need to write, if, for instance, if I want to model this as a linear program, I need to know how, is expectation of Q script of x omega a linear cost? Is it some h times transpose x? What is it? We don't have an understanding of that, right? All that we know is to compute Q script of x omega, I need to solve another linear program, right? So it's clear that if I have to solve another linear program, it's going to be impossible to encode all this information into that just like that. But that's where we build theory for this, okay? So the way so there are different ways to deal with this, okay? And I'm obviously not going to be able to go through all this in this course, but I want to give you an idea so when you leave this, you at least know the avenues. Later on, there are some avenues we'll discuss, others we'll leave untraversed. So more generally, what you notice is this problem can be just written as, if I bring the C transpose x in, is just the expectation of f of x omega, just some random function, right, over some closed and convex set. Okay, that's this problem, right? So yesterday we've been talking about deterministic convex optimization, right? When we talked about variational inequality, our game problems. I'm going to use this to start thinking about stochastic player problems. So yesterday, you remember we talked about this problem. This was our player problem. Okay? More specifically, we were looking at just this problem. Now I'm looking at this problem. So I'm replacing the. So now the problem is still deterministic in the context that f is just the expectation. But when I solve it, what is the big challenge? Why can't I apply deterministic methods to solve this problem? Why can't I? So one method I gave you yesterday was the projected gradient method. The projected gradient method said just take xk, subtract the gradient and project. Why can't I directly apply that method to solve this problem? What stops me from doing that? Yeah, Aruna?
I'm trying. Maybe the space of possibility, the space of events is not connected or is not smooth or something like that.
So the space is, so if we assume that the space is smooth, even if I tell you I give you a Gaussian distribution, right? I give you everything, I'll give you any distribution that you choose. The problem is that unless this expectation is easy to differentiate, computing this gradient is not easy. Because think about what the function is. The function is an integral over some probability measure, right? If it's a Gaussian, it's some nasty thing. If it's a uniform, it's less nasty, but it's still something. And now you need to differentiate that, right? So in general, you need to have access to gradients of integrals. And you need to have them fast, right? And that's hard to do. And so the way you get around that is here's a quick peek to what we do. Instead of, we just sample and we use. But if you use this, you need to have theory as to why this works and under what conditions it works. Recourse function and see whether it's got some structure that allows us to develop customized algorithms. We're not going to do that in this class, but just to give you an idea, in optimization, one of our foci is to actually get a structural characterization and develop customized algorithms for this kind of problem. Okay? Yes?
Doesn't sampling make the problem non-convex?
No. So all that sampling is doing is basically just pulling from the distribution, allowing you to take a step. From this standpoint, all it's doing, so when you sample, what are you doing? You don't have access to the true gradient, so you assume that you have access to the sampled gradient, right? And that's often the case. I can generate from the normal distribution, compute the gradient, right? Because the sample gradient is always easy to get as opposed to the true gradient. The true gradient requires you to integrate. Right? So the sampling is just an algorithmic, it's an aspect of the algorithmic structure. Right? The notion of non-convexity or convexity pertains to the original problem. I've not changed the problem. All I've done is I've changed the way I get a solution to the problem.
Probably I get it wrong, but based on my experience, it's like if you discrete, when I was sampling some problems, I was somehow discretizing them. And once you discretize, you need some integer variables to show.
So I think you're talking about something slightly different. So if you have were you talking about discretizing some sort of chance constraint using? So there are some avenues where if I have a chance constraint, I need to enforce a requirement that the probability of something is greater than something else. It's very difficult to get convexity there. So what you do is you actually generate realizations Say you generate 1,000 realizations and you want 990 of those to hold, which is like a relatively high percentage. But if you want any 990 of those to hold, then you need to use integer variables for that. So that problem becomes non-convex. The original problem is still convex, but you just don't have a way to characterize it. Okay, so I think we're talking, you might be, so we can talk offline, but I think might be.
Yesterday we talked about the Lipschitz continuous map.
Mm-hmm.
Here we have continuity or Lipschitz continuity of the distribution. Could you please elaborate the difference of these two?
So what I meant here was, and I'll talk about this as we proceed if we get to it, but essentially what happens is that q script of x is some function, right? Under some conditions of the second stage problem, you can show that q script of x omega minus q script of y omega is Lipschitz continuous. And the reason why this is useful, is if you have this, then you can invoke certain types of gradient methods. But it's not true in always. You need some properties for the Lipschitzian requirement to hold on the recourse function.
Yesterday we have it, but we had this. But now you differentiated continuity and Lipschitz continuity.
Yeah. So continuity is, so sometimes you have, so you always have the recourse function is continuous. This is a stronger requirement. So this stronger requirement comes from some properties of the second stage problem. So I'll go into those later. In general, if you're agnostic to this from a modeling standpoint, it doesn't really affect you. It affects you only if you're worried about developing algorithms that rely on sampling structures and some other decomposition structures. So it's basically just telling you, what it's telling you is that when you add this function, this recourse function, so if I tell you the first stage is convex and I tell you the second stage is convex and Lipschitz, assuming the first stage, so when I say Lipschitz, this is, I mean actually it's not q script of x omega, I'm sorry. I should be careful about this. I should really be looking at the subgradient of this. So let me go ahead and explain because I need more background to tell you what I'm doing. So whenever you have these gradient type methods, what you need is the gradients have to be Lipschitz. They don't have to be. If they're Lipschitz, it helps you. If they're not Lipschitz, you live with it. Okay. Now remember, because this function is non-smooth, you have to be a little careful when you talk about Lipschitz. So I have to be a little careful. So that's why I don't want to kind of say something until I give you a little more background.
Just one question for clarification. So when we choose the sampling method,
Yeah.
we end up with a scenario-based approach, right?
No. So when you use a sampling method, you assume that you can keep getting samples in the limit you get a solution to the original problem. When you use a scenario-based method, you generally generate scenarios ahead of time and you solve that approximate problem. So if you have an expectation, so if I have, well, I managed to lose the chalk. It's difficult to lose it. Oh, there it is. So for instance, if I have this problem, the scenario-based approach would replace it by this problem. And once I solve this problem, but there is still an error with this, right? A solution to this problem is not the same as a solution to this problem. Sampling methods will, in the limit, get you a solution to this problem. Scenario methods will always assume that either the original distribution only has a finite number of realizations, or I've taken a finite number of realizations and I use that as my representation of what's going to happen in the future. So if you assume that demand takes on 10,000 possibilities, and that's what you live with, that's okay. Now suppose it takes a different possibility, your model may not cover it. So you may not get feasibility with respect to that. So, but that's fair, because even in the sampling methods, you only get these answers in the limit. You have no way to deal with some of these things. So if you stop early, you obviously, in finite time, you're never going to be able to get a solution to this unless your problem is very well structured in some way.